So we've reached our last section of the course, which is section 9.5, which deals with solving exponential and logarithmic equations. All right. So this is something that you probably may haven't seen before, but really it comes down to the same basic idea that most equation solving does, the idea of using inverse operations to isolate variables, right? Because if you remember, that's pretty much the main idea of solving most types of equations. You want to isolate the variable, and how do you isolate the variable? You isolate the variable by doing all these inverse operations, like addition becomes subtraction, multiplication becomes division, so on and so forth. So the idea is the same with exponential and logarithmic equations. If you want to undo exponentials, you take logs on both sides. If you want to undo logs, you exponentiate, right? That's the word that we'll talk about later. You exponentiate on both sides. All right. So first off, what is an exponential equation? It's basically just an equation where the variable is at least part of an exponent, right? So if you have the variable up in the exponent position, that's going to be an exponential equation. All right. So I give you a little process here for this. I have it as a four-step process. And of course, to solve these, we're going to have to use logarithms, which is why we couldn't introduce them until after we had already introduced logarithms. So here's what you do to solve an exponential equation, right? The first thing, and this is pretty much a common theme in a lot of these types of equations we did, like absolute value equations was a good example, radical equations was another example. You want to isolate the exponential expression, right? Because if you remember when we did absolute value equations, we wanted to isolate the absolute value expression. When we did radicals, we wanted to isolate the radical expression. So here we want to isolate the exponential expression. And then once we've isolated it, we can use the whole idea of the inverse property, right? So, or the power property. It depends on what we want to, on what base we want to take. So we're going to take the log of both sides of the equation. If the base is 10, then of course we would use the common log because that has a base 10. If the base was e, then we would use the natural log because of course that has a base e, right? And then after you do that, you are either going to use the right? So after we take the log of both sides, what we're going to do is we're either going to use the power property or the inverse property, right? So this could be the inverse property. And actually, that's the preferred method for me, right? And I'll tell you what I mean by that when we go through the problems, and that's how I'm going to do the problems. I'm always going to use the same base log as was the base of the exponential. So we'll see that shortly. And then, of course, after you've used the power property or the inverse property, then the variable is now free. It's no longer in the exponent position. So then what you can do is you can just take, you can just solve, what's left normally, like a normal linear or yeah, generally linear, a normal linear equation, right? Where you just add, subtract, multiply, that kind of thing, divide. So that's pretty much your four-step process. And then, of course, what I do is I just give you a couple, right? So start with this one on the left here. 10 to the 3x plus 10 equals 1500. So where's the exponential expression? It's right here. It's 10 to the 3x. So our first step is just going to be to isolate that 10 to the 3x. So right now it's being added to, right? So to undo the addition of 10 to it, we subtract 10 from both sides. So now it's isolated because the 10 and the negative 10 cancel. So we just have 10 to the 3x equals 1500 minus 10, which is just 1490. Okay? Now that we've reached this point, what we're going to do is take the common log of both sides. Right? And remember, common log is base 10, and the reason we're taking the base 10 log is because the base of our exponential is also 10. So what I'm going to do is, how do I do that? I basically just write log in front of both sides, right? So I have the log of 10 to the 3x equals the log of 1490. And now the idea of this, again, is that these two things here are inverse functions of each other, right? Log base 10 and 10 to the power, 10 to a power, are inverse functions of each other, right? That logarithmic function and that exponential function are inverses, so they really just cancel each other out. just like addition and subtraction would do, or multiplication and division would do. So now what ends up happening is my left side, right, use the inverse property, is just 3x, right? So I use the inverse property to free the variable. The exponent was just 3x, and on the right side I just have log of 1490. Now you might say, well, why don't I put log 1490 into the calculator? We'll put the answer into the calculator later, but what we want to do is we just want to leave it in exact form for as long as we can, all right? So we have 3x equals log of 1490, and then now the last step was just solve this resulting equation. So here's my resulting equation, and I want to isolate this x, so right now it's multiplied by 3, so just divide both sides by 3. And now I have my exact answer, right? So x exactly equals the log of 1490 divided by 3, all right? So that would be my exact solution. But of course, you're going to want to approximate this, so that's where the calculator comes in, right? If I want to approximate this, what I will do is just do the log of 1490, close the parenthesis, you got to be careful there, right? Log of 1490 divided by 3, which is 1.0577, right? Depending on how many decimal places you're going to. So 1.0577, oops. So x is approximately 1.0577, and that would be my approximate solution, right? See how I have this little squiggly equal sign for approximate? So x is approximately 1.0577. So that would be the first one. And then the other one is a little bit more wacky, because you can see what you've got here now when you, in your exponential expression, it's 3.1 to the 2x, right? So what is 3.1 to the 2x? That's your exponential expression. So you're still going to do the same process we did earlier, right? We're going to isolate this first. So you're going to add 4 to both sides. So then we would just have 3.1 to the 2x, and now that's equal to 20. So now it's isolated. And now remember, I have 3.1 to the 2x equals 20. And what I'm going to do is take the log of both sides. But now since my base is 3.1, I'm going to take the log base 3.1 of each side. And is that a weird base to have? Sure it is. But it's still a perfectly valid base, right? Because we said you can have a log base any positive number, other than 1, really. Because it's just like exponential. You can't have a base of 1 because it's just a constant function then. So you have log base 3.1 of 3.1 to the 2x equals log base 3.1 of 20. And then again, the idea here was these two functions here are inverses, so they cancel each other out. So what do you end up with? You just end up with 2x equals log base 3.1 of 20. And now, just like the last one, that was my equation that no longer has exponentials in it. So to solve it, I'm just going to divide both sides by 2, and there's my exact answer. And that's perfectly acceptable as an exact answer, right? And this is the reason why I always like to take just the log of whatever base is currently in the equation, right? This was base 3.1. I just took log base 3.1. Now, depending on like who you talk to, some people will tell you always to take base 10 or base e, but I always like to just take the base of whatever the original base is. So in this case, it was 3.1. And I can still convert this on the calculator, right? Because if you recall from our previous section there, we had that change of base formula. And we remember that log base 3.1 of 20 is really log of 20 divided by log of 3.1. That was just my change of base formula. So really, log base 3.1 of 20 is actually that value there, right? Approximately 2.6478. And then I just have to divide that by 2, and I'll have my approximate answer. So here my approximate answer is 1.3239. So I've got 1.3239, and that would be my solution there. And I can do a check on this also. I mean, you can check it graphically if you want to, but more likely, just check it by substituting it back into the original equation, right? What is my original equation? 3.1 to the 2x minus 4 equals 16. So if I just go into the calculator and I do 3.1 caret parenthesis to the 2, not second enter, but second negative sign, right? You see the ants there is above the negative sign. So it's 3.1 to the 2 answer. And then I'm going to subtract 4 from that, and I should get 16, right? So it does, in fact, check. Right? And that's the nice feature of using that ants, is then you don't have to put the approximate value in, right? I don't have to type in 1.3239 because then it wouldn't give me exactly 16. Now, I mean, would it be close enough where you would tell that it was correct? Probably, but it wouldn't give you the exact value. Whereas when you use the answer key, it actually gives you the exact value. So that one does indeed check out. Okay, so that's the basic process of solving your exponential equations.